So we've talked about electric circuits and electricity in general. Now we're going to talk about electromagnetism and magnetism and the relationship between the two. We have a couple of different kinds of magnets. We have permanent magnets and then we have electromagnets. We'll talk about permanent magnets first. Every magnet has a north pole and a south pole, whether it's permanent or not. Like poles repel and unlike poles attract. You've probably had experience with this previously. So a north pole will pull a south pole towards it, and you can see here that there's a repulsive force between the two south poles in the diagram. These lines that we see are called magnetic field lines. So this would be an experiment where we've sprinkled some iron filings, and the iron filings have taken the shape of the magnetic field lines. Magnetic fields are invisible, but we can show them by using these iron filings. Like electricity, magnetism is not a contact force. It's a force at a distance. Something that fascinated Einstein when he was a kid. Someone gave him a compass as a gift, and he was obsessed with that force, this invisible force that he couldn't explain. So the region in space over which these forces act is infinite. The magnetic force never drops to zero, no matter how far away from a magnet you are. It just gets really, really weak when you get far away. And that region is called the magnetic field. So here we see a more detailed image showing some iron filings, and they show the magnetic field lines in a lot more detail. So you can see here that there's a curved shape to the magnetic field lines, like so. And there's a symmetry, which means it's the same on one side as it is on the other. And out at the ends, the magnetic field lines push out this way. But magnetic field lines are continuous, which means that there's no break in them. The magnetic field lines go around, out from one pole, and into the other. We can't see all these loops because the photograph is limited, but there's no break in any of the magnetic field lines. So when we draw magnetic field lines, we draw them out of the North Pole and into the South Pole. And again, they're continuous, so they go all the way through the magnet as well. So inside the magnetic field lines go from south to north. So they go from north to south outside. And so here we would have our South Pole. Here's the North Pole. So the magnetic field lines go from the north to the south, outside the magnet, but inside the magnet they go from south to north. So north to south outside, south to north inside. And every magnet has two poles. You can never have a monopole, mono meaning one. So we say that every magnet is a dipole. You'll never get a sale on monopole magnets. Looks like a good deal, but they don't exist. If you break a magnet in two, it still has a north and south. Each section will still have a north pole and a south pole. So you get two dipoles, and then four dipoles. So two, and then four, etc. It doesn't matter how we break it either. We could break it like that if we want. So why does this happen? Well, inside a magnet we have some special atoms, really, really small dipoles, and each of them has a north and south pole, and they're all aligned if we expose them to an external magnetic field. If we have an unmagnetized piece of iron, for example, the atoms would be arranged in a random way, and so they're not lined up, and so there's no magnetic field here produced by this piece of iron. If we magnetize a piece of iron, all those tiny dipoles will line up in the same direction, and that gives the piece of iron a magnetic field. We can knock the dipoles out of their alignment if we heat the piece of iron, or if we smash it with something, jar it with a force. or if we run a current in a particular direction around to force those atoms out of alignment. So there are several ways we can demagnetize a piece of iron. And over time, of course, those atoms will fall out of alignment if they're not exposed to a consistent magnetic field to keep them in alignment. So when we say that these are permanent magnets, really we mean they're semi-permanent. They'll keep their magnetic field for quite a while, but eventually it will drop and get weaker. So we can remagnetize a permanent magnet if we place it in a magnetic field. We'll often do this with a solenoid or an electric coil. We'll run a current, an electric current, through the coil and then put the magnet inside, and then we can line up all those dipoles again. It's called induced magnetism. So we're forcing the piece of iron to become more magnetic. Materials that we can do this with are called ferromagnetic. Fe might sound familiar to you because that's the symbol for iron in the periodic table. So this really means materials that are like iron. Iron is the most common, really good ferromagnetic material. You'll find it in iron ore, sometimes called lodestone. That's an older name for it. Cobalt, zinc, and nickel are also ferromagnetic, but to a lesser degree. They won't give you as strong a magnetic field. So if you're buying a permanent magnet, pretty good chance that it's made from iron. We also have what are called rare earth magnets, made from various materials, including neodymium iron boron, or Nib magnets. And these are very, very strong in terms of magnetic. You'll probably see these in some kids' toys, or any magnet that's small that's really, really strong. You'll also find these in computer hard disks. Not the new solid-state ones, but the older ones that are mechanical, that make the ticking sound when you're reading or writing to them as your computer's working. Those use magnetic fields to store data, to read and write. And so there's a very thin but very, very strong magnet inside those hard disks, and those would be rare earth magnets as well. Now we can generate a magnetic field using electricity. This is something that Hans Ørsted, a German scientist, discovered, kind of by mistake. He did an experiment where he passed current through a wire, and at first he didn't notice that there was any magnetic field using a compass because he had the compass lined up in the wrong direction. Then he turned it and started it like this, and then when the current was turned on, he noticed that the compass needles moved to be perpendicular to the wire. And so discovered that an electric current will produce a magnetic field. We can see here that that magnetic field is circular in shape, so it kind of wraps around the wire. Now when we describe these magnetic fields generated by electric current, it's kind of challenging because we need to be able to draw diagrams in 3 dimensions. So to do that, we'll use these symbols, and this symbol shows us something that's coming out of the page. So that could be current or magnetic field coming out of the page. And if we see an X like this, then that tells us that we have something going into the page. Could be the magnetic field or the current going into the page. Could also be the force, if we're talking about a magnetic force. So to show that, we use this to show the current going in or out of the page, or any of these other. And we can also remember the direction of the magnetic field using what's called the right-hand rule. We'll call this the right-hand rule number 1 because there are a couple of other ones we're going to see as well. So with the first right-hand rule, we point our thumb in the direction of the current. So you can see the current here. The current's moving up this wire, so our thumb points in that direction. And our fingers wrap around the wire to show the direction of the magnetic field. So our fingers are in the same direction as the magnetic field, like that. And you can see that the magnetic field is circular in shape, and the magnetic field is strongest really close to the wire. As we get further away from the wire, the magnetic field gets weaker and weaker, but it never drops to zero. Solenoids were discovered because scientists were looking for a way to strengthen the magnetic field. They noticed that if you just use a straight wire, the magnetic field is not very strong. If we wind the wire into a coil or a solenoid, the magnetic field gets much stronger. And that's because each of these wires generates its own magnetic field. And so if we add them all together, then we have lots of electromagnets working together, and we get a strong magnetic field inside and around the solenoid. This makes solenoids very useful for making electromagnetic machines like motors. The second right-hand rule tells us a little more about solenoids. Here we wrap our fingers around the coil or the solenoid to show the direction of the current. So the current in this case is going up on the front of the coil, and our thumb points in the direction of the magnetic field, which means our thumb points towards the North Pole, like that. And since current produces a magnetic field, that means that if we have another magnetic field interacting with it, there will be a force. And this is called the motor principle. So this arises because we have more than one magnetic field and they're interacting with each other, pushing or pulling on each other. Now we can also find the magnitude of the magnetic force acting on a wire that's carrying a current, because the magnitude of that magnetic force will be directly proportional to the current and also to the length of the wire. So we can write that here. There we go. So that tells us that magnetic force is directly proportional to, directly proportional to magnetic field times current times length. So those are the three factors that affect the magnitude of the magnetic force acting on the wire. Actually, this should go like that. There we go. That means directly proportional to. You may have heard of this fellow before, Nikola Tesla. There's actually a statue at Niagara Falls, Ontario, just across from the Table Rock. It's a statue of Nikola Tesla because he was one of the scientists that developed the electrical system that we use to get electrical energy from Niagara Falls. So he's quite famous, and you've probably heard of the car company too, named after Tesla as a tribute. So magnetic field is measured in Tesla. Those are the units that we use for magnetic field magnitude. 1 Tesla is actually equal to, or equivalent to, 1 kilogram Coulomb second, like so. Now, 1 Tesla is actually a very strong magnetic field. We don't often encounter a field that strong. The Earth has its own magnetic field, but it's much, much weaker than 1 Tesla. So the magnitude of the magnetic force acting on a wire carrying a current is also dependent on the angle between the magnetic field and the current. So we can, instead of using the proportionality statement that we saw earlier, we can use an equation. So here's an equation we can use. So we have the angle theta between the current and the magnetic field. And so when theta is equal to 90 degrees, you recall that sine of 90 degrees is equal to 1. And that's the biggest value that sine can have. So when the current and the magnetic field are perpendicular to each other, we get the greatest possible magnetic force acting on the wire. When theta is equal to 0 or 180 degrees, then of course sine of those values is 0, and we get no force. So the force is 0 between, or the force acting on the wire is 0 rather. Here is our third right-hand rule, and this is all about the force that acts on that wire, and we want to know the direction of that force. So we've just learned how to find the magnitude of the force, but how do we know its direction? Well, that's where the right-hand rule number 3 comes in. So with right-hand rule number 3, our fingers point in the direction of magnetic field. Our thumb points in the direction of the current, which is I, and the force comes out of our palm. So this is a three-dimensional rule. Let's try this one and see how we do. When you see V in these diagrams, V means the direction of motion of positive charge. So with these right-hand rules, we've been talking about conventional current, which is the flow of positive charge. Of course, the positive charges in atoms can't flow. They're protons and they're trapped in the nucleus. So when we talk about the flow of positive charge in a conductor, what we really mean is it's the movement of those gaps between electrons. If the electrons are moving left, then the gaps are moving right. So we can think of these V vectors as the direction of motion of those gaps moving opposite to the direction of the electrons in a conductor. So using the right-hand rule, the third right-hand rule, in the first one, if we draw, here we've got the motion of the current is upward, and the magnetic field is into the page. So we're missing the force. So the force, using our right-hand rule, the thumb points upwards, the fingers point into the page, and so we get a force that's to the left. So there's our force in this case. In the top right here, we've got magnetic field to the right, so our fingers point to the right. Our thumb on the right hand points upwards. So that means that the force is into the page. Remember, into the page looks like that, so that's what our force looks like in that case. Bottom left, we have our fingers pointing downward. We've got our thumb pointing to the left with our right hand, and so the force comes out of the page and is going to look something like that. And in the bottom right, we've got the magnetic field coming out of the page. We've got the current going to the right. So our fingers are pointing out of the page. Our thumb on the right hand points to the right. And we have the force is going to be upward in that case.